this video, we want to talk about modeling with exponential functions. So the idea is you're taking a scenario, and instead of coming up with, say, a linear model or a linear equation to model the information, you're trying to come up with an exponential model because you think it's a better fit. So exponential models look like y equals a b to the t, or y equals a e to the kt, or if it's a compound interest situation, you might do a times 1 plus r over n to the nt, and that's when it's compounding n times per year. Something that's good to know is that if you have what's called a continuous growth rate, of say 5%, it's saying you're using a compounding continuously and k is 0.05. But if you have an annual growth rate of 5%, they're saying you're going to compound it once per year, so n is 1, and r is 0.05. So the continuous growth rate would look like e to the 0.05t. The annual growth rate would look like 1 plus 0.05 to the t. And that's just some terminology that's used with exponential models. But we're going to go ahead and find an exponential model when we're just given 2 points, because sometimes that's challenging to wrap our head around, because we're not given what k is, we're not given what r is, we actually have to solve for it. So if we have to solve for what k and r are, we can actually use either form. We could use any of the three, but we're going to kind of stick to either the E form or the B form, the continuous compounding or just the standard form. And we could do it either way. And essentially what's happening is we have a bacteria population. It's 6 million after 2 hours and 54 million after 4 hours. And then it's asking us some questions about the model. How big is it after 10? When is it 100 million? What I would do first is just find the model. I want to find the population of this bacteria as a function of time t in hours. And I'm either going to write that as a b to the t or a e to the kt. And I can do either one. But the key is I have 2 points. I have after the input 2 hours, I've got 6 million. After the input 4 hours, I have 54 million. So I'm just going to plug in both of those points into my function, ab to the 4. And 6 is ab squared. I could do the same thing with the other form. And that doesn't obviously help me immediately, but the cool thing about an exponential is that if my first equation is equal and my second equation is equal, if I take one divided by the other, it should still be equal. So what I'm going to do is I'm just going to take 54 over 6 on the left side and ab to the 4th over ab squared on the right side. And that will make my a's cancel. 54 divided by 6, 9. I have b to the 4th over b squared is b squared. So it turns out, if I take the square root of both sides, b is 3. And so now I can at least say that p of t is a times 3 to the t. Now if I were doing this all with e instead, I would do that same process. I do 54 over 6 is a e to the 4k over a e to the 2k. My a's cancel. I get 9 is e to the 4k minus 2k, or e to the 2k. To solve here, I would take the natural log of both sides and then divide both sides by 2. So k is natural log of 9 divided by 2. And then I could write down p of t is equal to a e to the natural log of 9 divided by 2 times t. This is kind of my first step, is figure out what the base is or what the continuous percentage rate is. But I still need to find a, and the way I can find a is I just plug in a point. So if I plug in the point, let's say 6 when t is 2, so p of 2 is 6 million. At 2 hours I have 6 million. Then I can say that's a times 3 squared. So 6 is 9a. If I divide both sides by 9, 6 over 9 is a. So 2/3 is a. And p of t is 2/3 times 3 to the t. For this bacteria population. And this tells me what my bacteria is at every time t, where t is in hours. So if I had not done the a, b to the t form, I would do the same thing with the e form. So I'd say 6 is a e to the natural log of 9 over 2 times 2. 6 is a e to the natural log of 9. E to the natural log cancels because those are inverses, so I get a times 9. So 6 over 9 is a. So a is 2/3. And I get the same a, which makes sense. This is the same bacteria population. They shouldn't have different initial populations. It's just a different form of the equation. So these are equivalent. And I could pick whether I prefer a, b to the t, or if I prefer a, e to the kt. Once I have my model, so I would do one of these, not both. Once I have my model, then I'm going to answer my questions with my model. How big is the population after 10 hours? So I have to ask myself, what do I know? Do I know my input or my output there? Well, my input is my time, t in hours, so I know my input. And I'll go ahead and run with this first equation. So after 10 hours, I can just plug in 3 to the 10th. So if I plug that into my calculator, then I would get 2 times 3 to the 9th. And I believe that's 39,366 million. So this bacteria population is huge. Like absolutely huge. And this answers my first question, how big is it after 10 hours? The second question asks, when is the population 100 million? So now I want to know when when the population is 100 million. So when my output is equal to 100 million, and since everything's been done in millions, I'm just going to check when my output is 100. So I can multiply both sides by 3/2 to get 150 equals 3 to the t. I'll take the natural log of both sides, or the common log of both sides, either way, and that'll bring the t down. So I can divide both sides by natural log of t, and I'll get t is equal to natural log of 150 divided by natural log of 3. Now, a lot of times you're asked to solve in exact form. In a real world problem, you do want a decimal approximation, but you want to wait till the end because you don't want rounding error as you go. So if you take natural log of 150 divided by natural log of 3, I believe you get something like 4.56. And then I have to think back to my question, what are my units on my input? That's hours. So it's about 4.5 hours when it hits 100 million. And that answers both questions. Notice that when I'm doing models of exponential functions, what I want to do is I want to find my model first. My first step is just find this equation, because if I find this equation in one of these two forms, then I can answer any questions that's asked about the input or the output just by solving the exponential equation that I'm given, or by plugging in the input. If I'm asked to say when are two populations equal, I'd find models for both and then set them equal to each other. And that's using exponential models to answer application questions.